edge, and every clock cycle, okay, the input, the selector, okay, is sample, the 2-bit selector, and also there's input from out, okay, the external input, which is D. Okay, but the operation is depends on the selector. So let's look at the selector first. Okay. Oh, and remember, if we have a clear, okay, since the clear is asynchronous, right? So it will not follow the clock. So here it will be 0 because we have input clear here and here also. Okay. All right. Now, so the first operation is 3 or bit 1 1. Okay. 3. S1, S0, 3. So first is loading. And then 2 is complement. Then at this clock cycle, 2, so we complement again. At this clock cycle is 3 is loading. At this clock cycle, 2 is complement. At this clock cycle is 0 is preset. Okay, preset. And then clear. And then at this clock cycle, okay, S1, S0 is 3 is loading. And then at this clock cycle is 1 is shift left. Here also shift left, right? So we can fill up the hex value. Okay, let's use green. Okay, here it's clear, and then it will load D. Because D is A, so here is A. And then at this clock cycle, the next clock cycle here, okay, it will complement what is inside the register. So now the register has A, value A, or 1 0 1 0. So that is A. So we complement A and we will get 0 1 0 1 or 5. Okay. In hexadecimal is 5. And then we complement again in the next clock cycle. We complement again. So 0 1 0 1. Complement again and you will get 10 or A. In the next clock cycle we load. So we load 9. And then we complement 9. 9 is 1 0 0 1. Okay, we complement 9 and get 0 1 1 0. That is 6. Right? And then we preset. Okay, the next clock cycle we preset. Okay, so all bit, okay, all flip-flop will be 1. Will output 1. So that is F. And then we have clear. Then the next clock cycle, okay, it's 6. What we do? Oh, load. So we load 6. 6 is 0 1 1 0. And then we shift left. Okay, 1 bit. So it will be 1 1 0 0. Okay, or C. Okay, and then we shift again to the left. So 1 1 0 0. Shift again to the left, and you get 1 0 0 0. That is 8. Okay, so that is it for question 1. Any question? Is clear always asynchronous? Yes. For the flip-flop. Okay. How does synchronous clear looks like? Synchronous clear, you will know if we can see inside the flip-flop, which is we are not doing it at this level. So the clear will be asynchronous unless it is stated in the question that the clear is synchronous. All right, thank you, Masa, for the questions. Good questions. Others? All right. Okay, I want to continue with the next questions. So this one is accumulator. So this kind of question will also be in the test, accumulator. Okay. A 4-bit accumulator with mode control input signal perform function. Let me read again. A 4-bit accumulator with mode control input signal perform function. What kind of question is this? A 4-bit accumulator with mode control control the input signal perform function as in table 2. Okay, the carry in and carry out of the adder are not used. So we have adder here, and the adder is there is no carry in or carry out. Okay, coming, it's not used. And then what is it? We have mode. Okay, and mode. Okay, since this is adder and this is a mux, I think the mode will be here. The mode is the selector of the mux. All right. Now, what is it? Design the accumulator by completing the circuit in figure 2. Show the connections, the input value, and the primary input label. Okay, clearly indicates which connections are 4-bit wide. Clearly indicates which connection are 4-bit wide. I think you have to label if the connection is 4-bit. Okay. All right. Now, if mode is 0, Q is Q minus 1. Okay. If mode is 1, Q is 5. Q is 5. Oh, okay. So the output of the multiplexer will be connected to the flip-flops. Okay. And when mode is 1, Q is 5. 5 is 1, 0. Okay. 0, 1, 0, 1. So here we prepare 0, 1, 0, 1. Or maybe you can just write 5. But just want to make sure that this connection is 4 bits. Okay. You have to label this because it is what means by clearly indicates which connection are 4 bits wide. So this connection is 4 bits wide. So you have to do this. Okay. Same goes to this one. This is 4 bit. Probably this is also 4 bit. Okay. And then, all right. And yeah, this is 0101. So the other one must be from the adder. Okay, so this is also 4 bit. And the adder is performing Q minus 1. So this is Q. Q is going back to the adder. And okay, Q minus 1, okay, if you remember that we did in class, this is equal to Q plus F. So here you can prepare F or just write 1, 1, 1, 1. Right? So 1, 1, 1, 1 plus Q. So that is equal to Q plus 1. So that is connected with the mode 0. Okay. Oh, this is also 4 bit. Okay. So when mode is 0, Q minus 1. When mode is 1, it's 5. And then it will go to the flip-flops. Okay, and then that will be the output. All right, and then the output Z, so here we have Z, is asserted high, means Z equal to 1, when when Q3 to 0 is 0, means when the output is all 0. Okay. output is all 0. Okay. Construct the function inside the given dotted box using only one logic gate. So, okay, this is where we want to detect if the input is all 0. Means when all inputs, when all outputs are 0, okay, Z is 1. So Z is, okay, all output is 0 and complement. So this is a very common question to see all input is 0 or all input is 1. So if all input is 0, we use NOR. Okay, NOR. And this is only 1 bit, so we don't need to label that. All right, so I think that is all for these questions. No more questions, right? Okay, then there will be question 3. All right, so this is how we do question 2. Any questions? It's quite simple. Right? If there is no questions, I will proceed. Okay, I will proceed with the next questions. Okay, figure 3. Figure 3 describe the state diagram for finite state machine with input Z and input X and output Z. Each state is represented as Q1, Q0, and then we have to complete. I must have given you the wrong test questions, okay? Because this is supposed to be not filled, okay? This is supposed to be space where you have to answer it by yourself. Okay, but let's go through the state table. Okay, there are 3 states, okay, which is state 0, 0, and then state 0, 1. Okay, oh, that's that one. And then state 1, 0. And the other state is not used here, so just write don't care for the next state and D, okay, the input of the flip-flop, and also Z, the output. Okay, so it's a D flip-flop, right? If it's a D flip-flop, Q plus is equal to D. So these 2 columns will be the same as D1 and D0, right? So let me check. 1, 0, 0, 1, 1, 0. Yeah, it's the same. So it's the same. Q1, Q1, Q0, Q1 plus Q0 plus is the same as D1 and D0. Okay, so how to fill this one? Okay, when we are in state 0, 0, here in state 0, 0, when we are in state 0, 0, here, okay, the output is always 1. Z is always 1 during this state because this is more where the output depends on the present state. So when the present state is 0, 0, Z is 1. Okay, and when the input is 0, okay, from at state 0, 0, input is 0, the next state will be 1, 0. And if input is 1, the next state will be 0, 1. Okay, 1, 0, 0, 1. Okay, this one follows because it's the same. And then when we are in state 0, 1, 0, 1 here, the output Z is always 0. So output Z is 0. Okay, and when the input is 0, 0, 1. Is it not enough? 0, 1. Output is 0. So this is 0. I think I must have given you the incomplete questions. Okay, 0, 1. If input is 0, it's going to 1, 0. And if input is 1, oh, okay, it's not incomplete. Got it. Okay. There's no input written here because it's don't care. It's actually don't care. Okay, it's good that we do this exercise because I think I didn't teach you in the video lessons. So it's a don't care here. It doesn't matter whether the input is 0 or 1. Okay, it will go to the next state, which is 1, 0. Okay, when the input is 0, it will go to 1, 0. When the input is 1, it will also go to 1, 0. So it doesn't matter if input is 0 or 1, it will go to 1, 0. So it's don't care, but we don't write the input. Okay, instead of writing X, we don't write the input. Just go. Okay, we force the state to go to 1, 0. Right? Okay, that's interesting. Okay, now when we are in state 1, 0, okay, if input is 0, we go back to 0, 0. Okay, 1, 0. If input is 0, okay, go back to 0, 0. I draw another line for input 1. Anas, you just need one line here because it's don't care. Okay, doesn't matter if it's input 0 or 1, it's going to 1, 0. So we only need one transition arrow. And there's no input written there. Okay. All right. Coming back to this. Okay. When we are in state 1, 0. Okay. If the input is 1, we will go to 0, 1. Okay. And the output at the state 1, 0 is always 1. Right. So that is how we fill up the table. Okay. And then we want to derive. Okay, we can derive the equation by using the K-map. Right, so let's do the K-map for D1. D1 is Q1, Q0, X. Okay, this one is for D1. So it's 1, 0, 1, 1, 0, 0, X. Okay, 1, 0, 1, 1, X, X. 1, 0, 1, 1, X, X, 0, 0. Right, so there are two groups here, this group and this group. So your D1 will be Q0 plus Q1 bar X bar. And then for D0, we draw another K-map. Okay, the domain is Q1, Q0, X. Okay, for D0, it's 0, 1, 0, 0, 0, 1, X, X. So 0, 1, 0, 0, 0, 1, X, X. So the group is, yeah, So D0 is equal to Q0 bar X. And then Z, okay, this is more. So the domain is only the present state Q1, Q0. That this is D0. Okay, and it's 101X. Group is there. So Z is Q0 bar. Oh, and then we have to draw the circuit using D flip-flops and minimum logic gate. So I have asked the other lecturer whether they will accept if you just you didn't connect the feedback if the circuit is complicated, right? For this like this circuit, and they said yes, you can just draw the circuit without the feedback. Means for D1, first we draw the flip-flop first. Okay, we draw the flip-flop. This is, hold on. Okay, there's a flip-flop, two flip-flop. Okay, it has input D, and then clock, and then the clock is same. Okay, and then for D1 here, so we call this flip-flop 1 and this is flip-flop 0. Okay, so D1 here is Q0 or Q1 bar X bar. Q0 or Q1 bar X bar is looking like this. Q1 bar X bar. And then this is connected with OR. And this is Q0. Okay. And this one is Q0 bar X. So you don't have to do the feedback like this Q0 bar here. You don't have to draw it's coming from here. All right. You don't have to do this. Okay. I will accept just as like this. Okay. So in last class, last week, I say you have to draw the feedback. Okay. But I take that back. You can draw just like this. Okay. Let's save your time to answer the questions. All right. So you can draw like this. And I think that's it. Yeah. Oh, yeah. And Z. Okay. Z is just a Q0 bar. Okay. Okay. We can draw, this is Q0 and this is Q0 bar. And this one is connected to Z. Right? Or you can take this one and connect it with the inverter and that will be the Z. Okay, either one. All right. So that's all for question 3. Okay. If there's no questions, I will proceed since we already 9:40, and there's only one more question left. Yes, questions.
For Z supposed to be Q0 bar, not I mean to be connected to flip-flop 0, right?
Okay. Flip-flop 0. Thank you. Thank you, Anas. This is not Q0. This is Q1. It's Q1 bar. This is Q0, Q0 bar. So this will be Z. Right? Thank you very much. Okay. I will share with you the this paper that I have draw later. Okay. And then we have last questions here, which I think this morning Mushtaba asked me these questions. All right. So let's read the questions. The input L of the system. So we have this system here. Input L is here. Input L of the system receive logic 1 if the push button is not pressed. Of course, because this is a pull-up register here, we have a pull-up register where when there's no connection here, it is connected to the VCC. So it's connected to the VCC through the pull-up resistor. So L will be 1 if the button not push, okay, not press. Okay. If the push button is pressed, the input will receive logic 0. Okay, it's connected to ground this time. All right, design a state diagram for the system which output P high for 3 clock cycle. Okay, P will be high for 3 clock cycle each time its input receive a falling edge. Okay, means when this circuit detect falling edge, okay, when there's no button press, it always be 1, right? And then when the button is pressed, okay, L will be 0. L will receive 0. So when the detector, okay, this detector detect this falling edge, it will start output 1. Okay, P will be 1 here when it detects the falling edge. Okay, regardless of how long the input stays low. Okay, regardless of how long the input stays low, okay, it will be 1, P will be 1 for 3 clock cycles. Okay, the example that we did in class is it will be 1, okay, for 1 clock cycles, right? Okay, so this is in class example. Okay, but this one, it will be 3 clock cycle. First clock cycle, second clock cycle, and 3 clock cycle. 3 clock cycle will be 1, regardless of how long, okay, the button is pressed. Even though it is pressed for 1 second, press. Okay, maybe 1 second is too short. Probably it is pressed for 5 seconds. Okay, and the clock cycle is 1 clock cycle is 10 clock cycle, for example. But the detector, okay, the detector here can detect the falling edge, okay, even for a few seconds. All right, it will stay, P will stay high for 3 clock cycles. So how can we do the, how can we design the state diagram, right? Okay, derive the Moore state diagram. Okay, say Moore. So for Moore, we also have the edge. Okay, remember the in class example we have 1 and then edge and 0, right? Okay. Now for reset means if there's no button press. If there's no button press, L will always receive 1. Here. Okay. L will always receive 1 if there's no button press. So let's call this 1, just like the example in the class. And the output will be 0 because there's no button press. Here it will be 0. Okay. There's no falling edge detected. Okay. Okay. And then if we detect if the button is pressed, then if the button is pressed, L will receive 0. The button is pressed, L will receive 0. Here, 0. And if L receives 0, means we are in the stage for more. The system detect edge. And once the system detect edge, it will be output P will be 1. Output P will be 1. Right. So this is one clock cycle. Okay. So each state, okay, the state time is one clock cycle, right? So this state will be in one clock cycle. Okay. We want to hold one in 3 clock cycle. So next, we will hold. We will hold P. 1 clock cycle here, 2 clock cycle, and then we need another one. Hold again. Okay. Hold. Hold. So this is 3 clock cycle. Okay. Regardless of the input. So the input here is don't care. So we don't write anything. Okay. Either the button is push or not, here it will hold. Okay. The output P to 1. Alright. So this is hold for 3 clock cycle. And after that, it will go to stage 0. Okay, where the output will be 0. Okay. What is the input here? Okay, it is as if after the 3 clock cycle, if the button is still pressed, okay, if button still pressed after 3 clock cycle. Oh, it's 0. Sorry, when it's pressed, it's 0. Okay. If the button is still pressed after 3 clock cycle, means L is still receiving 0, but it's already past 3 clock cycle. Okay. When the edge is detected, P will be 1 for only 3 clock cycle. Okay, regardless of how long the button is pressed. Okay. Here, okay, after the edge is detected, okay, right away the button is not pressed, it will not go back to 1. It will still be, okay, it will still hold the output here. Okay, for after 3 clock cycle, okay, if the button is no longer pressed after 3 clock cycle, we will go back to 1. Okay, to state 1. If it's no longer pressing. Right? Understand, everyone? And then, what else? Oh yeah, 0. If it is still pressed after the after 3 clock cycle, if the button is still pressed, it will go to P will be 0. So we call that state 0. And after that, if it is no longer pressed, we'll go back here. No longer pressed, 1. And if it is still pressed, it will stay here, 0. Okay. There's no input written here because it is don't care. Or maybe you want to do like Anas, like this is for 0 and this is also for 1. You mean like this, Anas?
Yeah, yes, sir. Yeah.
Okay. If you are if you want to do this, I understand what you mean, but we can just use one arrow and no input as if it is means don't care, right? So if this kind of arrow coming out in the exam or test 2, it means don't care. It means don't care. All right. So let me write something here for those who are not listening to the class. Okay. No input because input is don't care. Okay, so that is all the discussion for test 2. Okay, thank you for Mujtaba for asking me this question this morning. All right, I have another video. Yeah, questions? Any questions? Oh, okay. Mujtaba was speaking. All right, so for I have another video. That is the exercise for the analysis of state machine. Okay, but I want to edit the video, but every time I edit the video, the apps crash. So I will resolve that maybe today or tomorrow and give it to you. Okay, so in Thursday I will record a video. I will record a video of the next chapter, which is the FSM controller. Okay, and I will give it to you on Thursday. But Thursday we also have tests, right? So maybe we can do another past year test. Okay, that is more recent. I will find it for you. I will do it first, and then we do it together. And yeah, that will be on Thursday, 9 a.m. Okay, so I'll give you a video on FSM controller, but we will do previous tests. Okay, on Thursday. And note that for milestone 5 and 6, I already give you which design that you have to do. It is the what is it? I forgot. The second one, right? GCD. Yeah, the GCD design. To find the GCD, Great Common Divisor. Okay, it is in the textbooks as what is written there. I think it is in the textbook. So just do that one. And if you think that is hard and in the milestone 6, I mean like in the CPLD, you can choose design 1 instead. Okay, but you will lose some marks as a trade-off because it is less challenging questions. Right? Okay, so any questions? I will share this one with you. This PDF that we discussed.
Yeah, doctor, I have a question.
Yeah, questions, Anas.
Yeah, because I don't have the textbook. Can you explain what is GCD?
GCD is a great common divisor that you can find it online. Okay, and you can ask the other friends to show you the textbook. I cannot show you the textbook because I can show you the textbook for the questions, but not for the notes because the owner sells the textbook. Okay, and it will be wrong if I share with you the textbook. Right?
Okay.
So
Yeah,
maybe you can
thank
ask your friends. Okay, the rest of the group member can find it together, or it's just a GCD. Okay, I mean it's in the textbook. It explains how to design. Okay, but you can design your own GCD by looking up on the internet because GCD is a common design for FSM. Okay, just type GCD FSM and you will see a lot of designs. Right?
Okay. Yes. Yeah. Okay. Thank you.
Okay. Okay. So if there's no more questions from your side, okay, I would like to end the class today. Maybe if you have question, we will discuss later in the WhatsApp. And this PDF I will share with you in the WhatsApp group. Okay, note that this is my answer. Okay, probably other class also discussing and they have another answer. Okay, if there is a conflict in answer that you know from your friends, please let me know. Okay, maybe I did some mistakes here because this is just my answer. Let me just write my name. So that people don't confuse this to the real answer scheme. All right, everyone. If there's no more questions, thank you very much for joining, and hope everyone have a.
Excuse me, doctor.
Okay, yeah.
Sorry
Questions?
for interrupting you.
No
I just have
problem.
one question.
Yes.
At what time exactly will be the test on Thursday?
Malaysia time 5 p.m.
Okay. Okay, thank you.
Tuesday, right? So it's just like the test one. Only
Okay,
the
okay.
test one we do it in Wednesday. So this one is Thursday.
Okay,
Alright?
doctor. Okay, thank you.
Okay. All right. So I hope you have a great week, everyone. So that's all for today. See you in another time. All right.